Okay, so last time we started F2. This was a ballistic pendulum. It wasn't a ball that's going to get hit a pendulum ball, but we have a dart that's going to embed into a block of wood or something. F2 in the NMSIs is always going to be your lab-based question. And so not all lab-based questions have you talk about the measurements or write out a procedure and such. These questions can actually vary. It could be, here's some sample data, analyze, okay? And so, but it's always rooted in a lab type experiment and focus on the data. Typically with those, what data do we need? How are we going to collect it? Is the focus of this problem. And so we drew out a sketch of the diagram that we'll see in the experiment. And by the way, they don't grade your art. They're looking for the basics. And so, and your labels, because when you say you're going to measure something, kind of give reference to your sketch. And then we got to explain how the student can use the measurements that were made in part A to determine the initial speed of the dart. And so I think we left off saying we need to consider the collision, and with collisions, conservation of momentum. And so, and there's a part two, there's the swing, because a lot of our measurements about height, angle, those were relating back to the swing. And so let's get it set up for both, okay? We want the initial speed of the dart. Well, initially, isn't that the only thing that has momentum? And so doing a conservation statement, in the beginning, it's just the dart. And I think they told us it's going to be moving horizontally before it goes into the wood. And so this isn't going to be like a projectile before the collision. It's not going to be a two-dimension collision. And then the block of wood is 0 if you want to put it as a placeholder. You don't have to. After the collision, what do we see? Both things. So it's going to be the mass of the dart plus the mass of the wood. And together they're going to have a final velocity. And here I go again, AC, after the collision. Y'all remember I used that last time? Did I? AC? Before collision? Oh, well, let's write it out. After collision. And so what we're trying to solve for or get to, not necessarily numerically solve for, but we want this initial velocity of the dart before the collision. And so we can get the masses from the scale we talked about. So check, check. Did we say we were going to measure the velocity of the system after the collision? Do we directly measure it? No, they said a timer is not available, so you can't measure that velocity. But if we take a look at the swing, is there something that we did say we'd measure that would help us calculate that velocity? Right. We said we could measure the angle, you can measure the height. And so kind of pause on momentum, switch to the swing. And so at the low point, and by the way, the swing, no more collision, but there's a height change. And so you want to consider that conservation of mechanical energy. Don't mishear me. I'm not saying kinetic energy is conserved. This is not at all an elastic collision. We're not looking at the collision at all when you look at the swing. Good? And so at the bottom of the swing, what kind of mechanical energy do we have? Kinetic. We've got kinetic. So it's 1/2, and this is the mass of the system, and this is the velocity after the collision. It's initial for the swing, but it's final for the collision. So this is that transitional speed that if you just go initial final, it may not dawn on you that it connects both of these equations. And of course, don't forget to square. And at the high point of the swing, or the top of the swing, max height, whatever you want to say, what kind of mechanical energy do we have? potential, gravitational, and it's the system that makes it to the highest point. Okay, so max height or HF, whatever you want to call that there. Really, in my diagram, I said HF, so I should be calling it HF, right? For consistency. So I just added the F there. And so what do you notice in our energy statement? Right, it's both masses included, so it does cancel in both. And we would be using this equation to learn something about that final velocity after the collision. And so I'm going to solve for V, multiply both sides by 2, take your square root. And so we measured HF. We know gravity. And by the way, in a lab-based situation, a good rule of thumb, what should we use for gravity? 9.8 is more real life, right? 10 is just a quick estimation to make the test go quicker, okay? But in real life, you know, when we do labs, 10 really, I mean, gravity really should be 9.8, okay? And so that would help us get the velocity after the collision, which would help us then solve for the initial velocity of the dart, okay? So they do say the verb explain, and I don't harp on the verbs a lot, but as we approach the AP exam in May, if they say explain, yeah, I have a justification here, talking about the variables and what's measured. Oh, I guess we can add in that the masses are measured, right? Measured. Okay. And so every variable is either a known gravity or it's a measurement. And then we calculate that after collision velocity and use it to get the final answer of the initial velocity of the dart before the collision. Now, if they say explain, we should give maybe at least one summarizing statement. And so kind of what did we do? What's the big ideas here? And so using conservation of energy, student can use the measured height, final height really, to calculate the velocity after the collision. Then use conservation of momentum and just to reiterate, we measured the masses to calculate the initial velocity of the dart. Good deal? Oh, other way. I have to shrink it so it'll all fit. So it's just a good rule of practice or rule of thumb that if they say explain, maybe they really are looking for some words, but typical physics, you can give justification with physics principles, okay? So you can support it that way. Even on the paragraph response, you can have justification with physics, but I would end the paragraph one with maybe 3 sentences, since that's kind of their absolute minimum. Good deal? All right, C, the student is not able to vary any, oh, by the way, did I use angle at all? So we talked about you could measure angle, but if you measure the height change, I really don't need the angle. Now, maybe that was all that I could have. Maybe there wasn't a meter stick or ruler available, or you could say maybe the neighbor next to you says use a protractor and you measure the length of the string and then you can calculate the height change. But like our simulation, I mean, they did say a meter stick was available, right? Yeah, so you could get the height change just like we did in the simulation. So just because a protractor is available doesn't mean you have to use it. Your neighbor might, but you may not, okay? So it's just giving you options, but definitely don't use a timer. They said that wasn't available. Okay, so the student is not able to vary any aspects of the crossbow. They can't change the spring loadedness. They can't, change the mass of it or the dart or the hanging block. Explain how the student can obtain more precise measurements of the speed of the dart. Now, careful, they're not measuring the speed of the dart, but they're taking measurements that'll help them get the speed of the dart. What does a good scientist do to have more confidence in their data? Multiple trials. Y'all, that's the one thing they're looking for here, okay? And so multiple trials. And then the student would do what with the data? Maybe your measured heights, average, 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 the multiple heights. And by the way, chances are you don't need to weigh the masses 3 or 4 times, right? Because it's going to remain at rest. But with this block swinging, think about the sim, right? And so you may need it to swing a few times to get that actual height, a more precise height. Average the multiple heights and then calculate VI of dart with the average. But the big thing there, you may not need all those parts for the points, but the big thing is a good scientist does multiple trials, right? Even your top scientists, they don't say, I am perfection. I do it 100% the first time. No, no. Okay, I think there's a part 2. Yes, there's more. And so on the next page, now we get into those system aspects, okay? Let E represent the total mechanical energy of the dart, block, earth, system. How does the value of that mechanical energy change as the dart becomes embedded in the block? And yeah, we have a checkbox, but let's focus on the mechanical energy during the collision. Don't worry about checking the box. Get your justification first. What's the physics here? When it embeds, what kind of collision is it? What kind of inelastic? Perfectly, completely. And so it's that completely inelastic collision. And what do we know is true about mechanical energy during a completely inelastic collision? It's not conserved. Far from it. Kinetic energy is lost, and I put that in quotes because I hate that like energy is converted, energy is transferred. It's not really lost, but I know it's very common to say that. So it's transferred into what? Where does it go? Heat within the system. There's no surface this is sliding on. And so kinetic energy is transferred to heat, and that's internal to the system. And so if we know the kinetic energy decreases, how are we going to check the mechanical energy question? Doesn't change into potential, right? That's the other form of mechanical. How are we going to check the box? Decreases, okay? No, just how, since the earth is included, we can talk about potential, but it's not like the kinetic energy lost in the system converts to potential. So we can't check it's the same. And so it's going to decrease. What about how does the value of mechanical energy change as the dart and block swing upward to their highest point? Well, this is after the collision, and so it's just the dart and block during the swing. So mechanical energy would stay the same if you include the earth. And so during the swing, the mechanical energy at the bottom equals the mechanical energy at the highest point or top when you neglect what? Air resistance, neglecting. I mean, I don't think you have to put that. That's one of the AP assumptions. And OneNote has quit writing. Give me 1 second. No, this part B is after the collision.
So you recognize it's long, but then you still.
But after the collision, whatever mechanical energy you have is going to remain during the swing. So part 1 was about the collision, part 2 is about the swing. And so what was I writing? During the swing, mechanical energy at the bottom and mechanical energy at the height are equal. And you can add in, if you want, neglecting the air resistance. Okay. The kinetic at the bottom transfers to gravitational at the high point. Good deal on that one. And then part E, similar but different. We still have a system approach, but now this isn't an energy question. They're asking about the momentum. Let P represent the total vector momentum of the dart block system. So the Earth is not part of our system here. Does momentum change as the dart becomes embedded in the block? Now this is just a yes or no question, but again, most of your points are going to be in that explanation. So does momentum change when it becomes embedded during the collision? No. And so it does not. Now explain your reasoning. And so in an inelastic or a perfectly, either way, inelastic collision, total momentum is conserved since there are no, do y'all remember the caveat to conservation of momentum? No external forces do impulse on the system. I don't know if do is the right verb there, but that's all I got right now. Impart would be like a fancier word. Impart an impulse to the system. And you're like, well, what about the heat loss? Y'all, heat is energy. Heat is not momentum, okay? Heat is joules, okay? And so, yeah, there's a heat loss, but there's not an impulse during the collision. What about, does momentum change as the dart and block swing upward to the highest point? So this is the swing. Does momentum change? It goes up, 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 up to a velocity of? Yeah, so how does velocity approach zero? You still have, that would be zero momentum at the high point. And so P final would be zero at the high point. It does change. Why? After the collision, is there an external force to the dart block system that's causing an impulse on them? Gravity. Gravity is the big one, bringing it to a stop. And so, yes, so during the swing, gravity, and I'll use my fancy word here, imparts an impulse on the dart block system to slow it to a stop, slow the system to a stop at the highest point. And in both of these, I'm envisioning like a picture you could do to help support, but it's not required. Good deal on that? Okay. The next one is commonly missed, just FYI, okay? Suppose that rather than becoming embedded in the block, the dart bounces backward off the block. Will the block swing to a higher point, lower point, or the same point as the dart embeds itself? Oh, as compared to when the dart embeds itself in the block. So you're comparing a bounce to an embedding. And so you got a checkbox there, but focus on the physics here. And I'm going to give you, 2 minutes as a small group. Okay. Think about comparing a bounce to embedding. Okay. 2 minutes. Think about it, discuss it, and then we'll go over real quick. So what do we think? High, low, same. You say higher? Lower? Okay. Any votes for same, right? If you wait long enough, someone will vote for every single one, right? So higher is the correct one, but your points go into the explanation. So why does it go higher? Uh-oh. So yeah, the end of our solution, if you have a higher gravitational potential energy, it has to come from a higher kinetic. And these were for the system in the swing. So that's the end story, true. But why does it have more kinetic energy? And by the way, oh, no. It's not the system swinging up now. Doesn't embed. Who's the one moving up? Just the block. So this is a block only swinging up. And it's not, the answer is not because it's less mass. That's why it has higher speed and such. It's perfectly what? Well, I wouldn't make that assumption. So the AP rule of thumb, don't ever assume it's perfectly elastic unless told otherwise. Because your perfectly elastic examples are going to be your Newton's cradle. It's those heavily dense objects that don't change shape. Do you think maybe, even though the dart, maybe it has a pointy end, but if it bounces off at a high speed, it's probably going to put a dent in the wood, right? So I wouldn't say elastic. So if it doesn't embed and if it's not elastic, what's your in between? What can you assume? Partially inelastic. Okay. Now let's talk about the momentum there. And so your M dart, VI dart, well, I don't know if it said it, but we can assume you don't want to make too many changes, right? And so here we'll assume that the dart's going to start with the same momentum. Let's assume your block starts at rest again, but now they're going to be not sticking together. And so now massive dart has a final velocity separate than your wood. And if the dart bounces back, what do we got to do differently here? Negative. What's negative? What about the dart? The final velocity has to be negative. And if we're trying to solve, because the block only is going to the swing, if I want to solve for that last piece, okay, what do we got to do with the final momentum of the dart? I got to move it to the other side. So if it's negative on the right, we got to add it to both sides. Okay, or it should cancel out like that. And when you do this, yes, the wood is the bigger mass, but your change in momentum for the dart, your change in momentum for the dart is going to be greater now. And during a collision, what's true about the changes in momentum of your two objects? Well, it's equal. Yeah. Conserved, same spirit, but wrong choice, I guess. So in a collision, dart hits block, block hits dart. The dart has to not only, the Newton's third law, equal and opposite. And so during the collision, The change in momentum of the dart is equal and opposite to the change in momentum of the wood. And the mass of the wood is the same as before, right? But now your change in velocity of the wood is going to be greater. So that greater speed after the collision, so V final after the collision is now greater. And so the block of wood or block will reach a higher point, which is, I think, what we had to check, right? Does it go to a higher point, lower point, or same point? Good deal. So bouncing, not only is a change in magnitude, it's a change in direction. Bouncing imparts a greater impulse on both objects. Good deal? Okay. So that's F2. It wasn't, you know, our previously seen ballistic pendulum, but whenever you have that conservation of momentum due to the collision, and then there's a height change where you got to do that, that's kind of the ballistic pendulum idea. Good deal? All right, one more, I think, is what we'll have time for. And so F3 we'll do together. F4, if y'all want to try it, this is the infamous, and I don't know how often I've said it, but a few years ago, 2015, 16, AP put speed bumps on a ramp. And everybody like went to Twitter afterwards, like, what? By the way, don't go to Twitter after the AP exam. You got to wait, right? You can't ever discuss multiple choice. Teachers don't even get multiple choice. But free response, don't tweet. They are checking Twitter. They penalize you from discussing the test when you're not allowed, okay? Note to self. But speed bumps on a ramp. Teachers typically, they've never done that before the exam. That's here because this was created afterwards. And so if you want to try this one to kind of test your knowledge about speed bumps on a ramp, this could be some independent practice, okay? And so we're going to take a look. I told you the rain question on my bell ringer. We were going to see one similar. This one, not rain, blocks. A cart of mass M rolls with an initial speed, VO, on a frictionless surface. Oh, frictionless bearing. So that's the rolling of the wheels. There's no losses in the wheels. The cart has 3 slots that fit 3 identical boxes, also M each. So our big cart has the same mass as one little block. Got it? Material density, you get it? Okay, crazy. The cart moves beneath a dispenser that drops one of the boxes directly into each slot. So I'm thinking this is perfectly timed. This is like a factory. They're filling something up, right? Okay. The first box drops into the cart at T1, the second box at T2, and the third box at T3. On the grid below, draw a graph, your favorite thing to do, of the cart's speed as a function of time. Label the relative values, relative. You don't have to get it, you know, on the exact number. There's no numbers on this graph, but relatively speaking, try to be in the right region. For VO, T1, T2, and T3. And so it's a velocity time graph. What you don't do is say, oh, it starts with an initial velocity. They said it's constant. So my velocity must be constant the whole time, right? Now you could argue that to be true if the cart was much more massive, right? I'm thinking it's a real heavy metal type of cart and we're just dropping little pellets of sugar or, you know, a little tic tac in each one, right? It's not going to change much. It's still technically physics, it would change. You are adding mass, right? But that would be your closer to constant velocity. But here it's equal mass. And so kind of similar to the rain question, after the first drop, and so let's kind of do this. Is it going to start out the fastest or the slowest? Fastest. So maybe we put our initial velocity, the fastest it's going to be, okay? And if you want to go up to that other one, I literally, I didn't count the boxes. It's the fastest. Timer starts. It's moving. It's going a constant velocity for a little bit of time. And then M block drops in. So T1. What's going to immediately happen to your system, to your cart, when your mass doubles? It's going to go down. How much? Let's prove it. We got some space. Let's actually prove that it's going to go half. It's a collision, right? It's a change in momentum.
What did you do for?
Hold on, let's do it. And so here we start out, what has momentum? The cart. So I got MVO. After the collision, what's our mass? 2M. Let's solve for VF. So M's cancel. VF would equal VO over 2. So yeah, it does go to half. And so ish, half. And if you want to count the boxes, you can. And so it's an immediate change in physics land. Okay. Technically, there'd be a small diagonal, but it's super steep. And then it's going to travel slower. Is it going to all happen in equal timing if you're now traveling that same distance? Okay, the same distance based on the picture, your block of wood spaces are equidistant, right? And so if you're now going slower, the next time one drops in, is it going to be equal time or longer time? And so maybe we travel a little bit longer at that half speed. And then the next block drops in at T2. What velocity do we go to then? Does it go in half again? Let's test it with our conservation. And so I'm going to go back to the very beginning because frictionless bearings, momentum is going to be conserved with every drop, yes? Okay, so I'm just going to go back to the beginning because it's a little easier. But after the second block drops in, what's our system mass? 3M. Same story, mass cancels. What's my new velocity? V over 3. So it's a third of the original. And so if you want to convert kind of to decimals or eyeball, maybe a third. Okay, VO over 3. And it's an immediate change to that new velocity. How long, what time passes before the last block is dropped in? More time. So just extend it to more time for T3. And then when the third block drops in, our total mass is 4M. And so my final speed would be a fourth, so estimate or count it out. And so we'll drop down and then continue on, right? Until something else happens. Good deal? Kind of, but not a curve. Not a curve, because there's time where it's not receiving a change. Okay. And technically, we already did this part. B, in terms of M and VO, write an expression for the final speed of the cart and boxes after the last block. So that's the one I didn't do. But we could say, MVO equals total mass, what did we say? 4M, and that V final that we're looking for. And we want to solve for that in terms of M and VO. Well, M still cancels out. And so it'd be VO over 4. That's it. Would the final speed of the cart be different if the slots were spaced closer together? So imagine if they were closer together? If so, how would the speed be different? And in either case, explain your reasoning. So if the slots were closer together, would the final speed be any different?
No, it's the same mass.
It's right. So your final speed that we just calculated, did we ever consider the distance they were spaced? No, it was mass dependent, initial momentum dependent. And so would the final speed be different? No. VF of the system maybe depends on initial momentum and the masses of the boxes, not the spacing, distance. In the cart. Now, the different spaces would affect what? It would affect the timing of it all, right? So if they were closer, you're gonna have to drop them quicker and it would scrunch our graph, right? But in terms of that final speed, the distance doesn't matter. Okay. Another student works with a cart of mass M, but it's much longer and has many slots that can carry boxes. So many slots, I'm assuming they're implying more than 3. The student suggests that if enough boxes fall into the cart will eventually come to rest. Is the student's hypothesis correct? Why or why not? Yes. Yep. Keep going, yeah.
It would not, because it would be fraction of the original speed.
Why?
Because
Conservation of momentum. Yes, that's perfectly right. Okay. And so the student said it would come to rest. Is the student correct? No. The system will never come to rest due to the conservation of momentum. Conservation of momentum. But as mass increases, the speed, and we can say the word, like you said, exponentially. Exponentially, hopefully that's spelled right. The speed exponentially decreases or gets closer to 0, but never 0. Hercules what?
So there was a
Uh-oh.
that back in, I want to say, Greece, famous mathematician proposed is Hercules ran at 2 miles within an hour, and the snail approached him at, let's say, half a mile in 2 hours. The distance would always close, but never be 0.
Right. Yeah. I thought you were going to go chemistry on me and talk about the half-life decay. Do y'all learn half-life in chemistry anymore? Okay. I don't get to talk chemistry much anymore, but yeah, it's always going to approach 0, but never get to 0 unless we'd encountered some kind of friction, right? External force that would bring the system to a stop. Okay. They didn't introduce that. Good on that one? All right. Now for the part that we haven't done a lot of, but again, as the AP exam gets closer, we got to get ready for this. Get ready for an equation you've never seen. Get ready for an equation that is going to blow your mind. You're going to be like, my teacher never taught me this equation. I've never seen this. This equation is not on a formula chart. How am I supposed to answer this question? Y'all, relationships. It's all about the relationships. We've done that a lot, right? These 2 variables have a direct relationship, an indirect relationship, okay? And there's not any numbers here, And so focus on the relationships here. I promise, if you look at all the grading rubrics, most of them can be answered if you just look at the relationships of the variables mentioned. And so there's 4 here. How about we do 2? Y'all do 2. We'll do that. We may only have time for 2. So now the students are given a new situation in which the cart of mass MO, capital MO, and length capital D. Notice it doesn't have slots. It's just an open cart. It's underneath a device dispensing water or, whatever, sugar instead of Tic Tacs, right? Maybe it's a pixie stick filler upper. I don't know why I'm thinking candy. Sorry. The water passes through a hole in the track except during the time that the cart passes underneath the device. The mass of the water that empties into the cart every second is R. R. Let's read that a little slower. The mass of the water that empties into the cart every second is R. Now, it's not random that they chose R. Do you hear mass per second? This is a rate, okay? It's a flow rate type. And so R, if you read it carefully, it's mass per second. Unit would be, how about kilograms per second? Okay. The cart's initial speed before passing beneath the water is VO. And we know from before, as water fills up, what should the cart system do? Should slow down, right? Okay. A student observing this situation suggests that the final speed of the cart after it leaves the water's downspout is given by the equation VF equals VO, the initial velocity of the cart, minus RD over M. R is the flow rate, D is the length of the cart, and MO is the mass of the cart without water. Everybody good? You've never seen that before. Is it reasonable for the quantity R to appear in the numerator in this equation? Why or why not? So let's see. If you look at that R, it's a numerator of a fraction, right? And so as R increases, what happens to that fraction? RD over, and you have to assume that the MO and the D remain the same. The initial velocity is the same, right? And so as R in the numerator increases, what happens to the fraction? Also increases. And does it make sense that when that fraction increases, then VO minus that fraction would do what? Your VF would, if you subtract a bigger number, you're going to get a smaller VF. Does that make sense? The more you dump into your cart, it's going to slow it down quicker, right? And so, yes, it makes sense. And notice I didn't write the words direct and indirect. That subtraction kind of throws that part off, right? And so the VO is a full number. It's not going to change unless told otherwise. But we still are looking at the relationship in terms of increase within the fraction. But I can't just say, oh, R is directly proportional to VF, okay? You don't want to say something like that if there's a add or subtract. 2, is it reasonable for the quantity D, the length of the cart, to appear in the numerator in this equation? Why or why not? So let's look at the relationship. So what if D increases? In other words, what if it's a longer cart? Same story, right? The fraction would also increase. Therefore, VF would decrease. When you subtract a bigger number, VO is the same, right? And so does it make sense that if the cart's longer, it's going to accumulate more and slow down the whole system? Yeah. And so, yes, makes sense. More water added over a longer distance would slow the system. Good. All right, we got a little bit of time. How about y'all try the last two? Okay, so I'll give you about 5 minutes to do both. Maybe it doesn't take that long, but have some discussions, right? Consider both possibilities and then which one makes more sense. And then we'll go over right before pledges. All right. Okay, so what did y'all think on part 3? Is it reasonable for the quantity MO, the mass of the cart, to appear in the denominator in this equation? Why not? Well, you got to focus on their equation, right? So VF equals VO. And then if the mass of the cart was bigger, oh, hold on, I can't listen to 2 at once. So if MO increases, what does your fraction do?
It decreases, which doesn't make sense because it's adding more volume to it.
Well, this is just about the mass of the cart. No, they're just saying, I'm saying play the relationship game, right? Why does it make sense that it's in the denominator? And so if MO did increase, the fraction would decrease. You'd be subtracting a smaller amount and your final velocity would be higher. And so does that make sense? I can't hear you.
It would make sense to me. Would it make sense for the cart to get faster?
Right. And so, yes, now you could talk about as you add water the whole time, okay, you're not changing that flow rate, but it should still decrease as the system moves on. And so it's contradictory here. And so, didn't finish. Okay, so real quick, here's just the NMSI key there. So what we got, fraction does get smaller and subtracts less from the initial speed. But if your cart's heavier on its own, it has its own inertia. And it says sand. I don't know why it switched from water to sand, but ignore that. So it's going to have less effect as you drop sand water in. It's going to continue, right? And so the heavier cart, the harder it is to use the sand to slow it down. Okay. And then the last part, what part of the equation makes it impossible? Well, if you add enough water, if you make the cart long enough, if you make the cart heavy enough, you could subtract a full fraction, right? And get a final velocity of 0. Should that happen? No, go back to that. It's exponentially going to decrease, but never approach 0. Okay, now I feel better. Y'all have a good weekend. I'll see you Tuesday for the exam.